You might think, with quantum computing and all the wild stuff in modern physics, that classical physics is kind of obsolete, gathering dust somewhere.
Yeah, like a museum piece.
Right. But here's a twist. A lot of the tech we rely on every day, think GPS, lasers, it's actually powered by principles straight out of classical physics.
Absolutely. Classical electromagnetism, mechanics, they were still incredibly relevant. It's kind of the surprising staying power we want to unpack today.
Exactly. So this deep dive is all about why classical physics isn't just a history lesson, but actually a vital foundation for understanding the universe around you right now.
And it's fascinating, isn't it? Even with relativity and quantum mechanics changing the game, classical physics still gives us the basic language, the framework for so much.
The core concepts, space, time, force, energy, they're still indispensable tools.
They really are. They inform even our most advanced thinking.
Okay, so that's our mission for this deep dive. We're venturing into the foundations, the philosophy, really, of classical physics.
And our guide for this is that document, lec1.introduction and history.pdf. It's our roadmap, basically.
Yeah, it covers the history, the key ideas, and those links to modern physics and even philosophy.
And the goal here isn't to get bogged down in, tons of math.
No, definitely not.
It's more about distilling the essence, tracing the roots back, especially looking at Aristotelian physics, which is crucial context, and just grasping its lasting influence.
A shortcut to the core insights, essentially.
Exactly, getting a solid handle on these foundational ideas.
So this term classical physics, you said it's not just about being old. What really defines it then?
Right. So fundamentally, classical physics covers the theories that came before quantum mechanics really took hold in the early 20th century.
Okay.
But classical here refers more to its conceptual structure, how it approaches describing the world, its methodology, rather than just its age.
Got it. So method and structure, who are the main players? What are the big theories in this classical toolkit?
Well, the absolute cornerstones are Newtonian mechanics, and that includes its later forms, like Lagrangian and Hamiltonian mechanics.
Okay, Newton.
Then there's Maxwell's theory of electromagnetism, which was huge. Thermodynamics, too.
Right. Heat, energy.
And interestingly, even Einstein's special and general relativity, though they came later, around the time quantum ideas were emerging. They're still considered classical in their basic structure. They don't have that inherent quantum weirdness,
Oh, okay. So even relativity fits under this classical umbrella, structurally speaking. Fascinating. So these different theories, Newton, Maxwell, Einstein, what ties them together? What makes them all classical?
There are a few key characteristics that most of them share. One big one is determinism.
Determinism meaning?
Meaning if you know the exact state of a system right now, every position, every velocity, you can, in principle, predict its entire future perfectly.
The future is locked in by the present. Okay.
Then there's time reversibility. Generally, the fundamental laws work the same forwards or backwards in time. You could run the cosmic movie in reverse, and the physics would still make sense according to the laws.
Okay. Like rewinding a film?
Kinda, yeah. And the third big one is locality.
Locality, no spooky action at a distance.
Exactly. Interactions happen through direct contact or via fields like electric or magnetic fields that have to travel through space. Nothing jumps instantaneously across a distance.
Determinism, time reversibility, locality.
Got it. So when classical physics builds its picture of the universe, what are the fundamental building blocks? What's in the inventory?
At the most basic level, it's about interacting entities. In Newtonian mechanics, the stars are really particles.
Point-like things.
Yeah, think of tiny points with properties like position, mass, maybe electric charge. Very particle-centric.
Okay.
But then in Maxwell's electromagnetism and also in thermodynamics, fields become much more fundamental.
Fields. Like invisible influences spreading through space. Exactly. Continuous things spread out everywhere, electric fields, magnetic fields. They're not just effects of particles, they're entities in their own right.
Right.
And then general relativity adds another layer. The metric. The metric, what's that? It basically describes the geometry of space-time itself, how we measure distances and time intervals. And the key thing in GR is that this geometry isn't fixed. It's dynamic. It changes based on mass and energy. It's like the fabric of space-time itself is a physical entity.
Wow. So particles, fields, and the space-time fabric itself. And these things interact according to rules, evolving over time. Sounds very orderly.
It aims to be, yes.
Yeah.
And to handle this mathematically, classical physics uses the concept of the state of a system.
The state, like its current condition.
Precisely. Think of it as a complete snapshot at one instant, a mathematical package holding all the relevant info, positions, velocities, field values, everything needed to describe it fully at that moment.
Like hitting pause and writing down all the details.
You got it. And the state space is simply the collection of all possible snapshots, all the potential states the system could be in. Often, mathematically, it looks like a vector space.
Okay, a space of possibilities.
And the system's evolution over time is just seen as moving through this state space, tracing a path from one state to the next.
So what dictates that path? How does it know where to go next in the state space?
That's where the dynamical laws come in, or laws of evolution.
Rules of the game.
Exactly. A dynamical law is just a rule saying, if you're in the state now, you'll be in that state next. It dictates the sequence of states over time.
And these laws are universal.
That's a key assumption, yes. The same laws apply to all systems of a certain type, everywhere. And crucially, the laws usually depend on the underlying physics, not just how we choose to write down the coordinates or describe the system.
Universal rules moving things through this space of possibilities. It feels a bit abstract. Can we make it more concrete? Maybe a super simple example.
Sure. Let's take a coin. Simplest case.
Right.
It can be heads, H, or tails, T.
Okay. State space is just H. Two options.
Exactly. Now, what could a dynamical law look like? Let's imagine two weird coins.
Right.
Coin 1, if it lands heads, it always stays heads next time. If tails, it stays tails.
Okay. Boring coin. It never changes.
Right. Coin 2, if it lands heads, it always flips to tails next time. If tails, it always flips to heads.
The flipper coin. Got it.
Mm.
How do we write that mathematically?
We can use a variable, say sigma. Let C's plus 1 mean heads and 9s1 mean tails.
Okay.
For coin 1, the boring one, the law is just sun plus 1.
Right.
The state at the next step, n plus 1, is the same as the current step.
Makes sense.
For coin 2, the flipper, the law is n plus 1 and enton. The state flips sign at each step.
Simple enough. And in this case, just knowing tells us everything, right?
Precisely. Only one variable is needed to fully specify the state. We say this system has 1 degree of freedom.
1 degree of freedom. Cool. Let's make it slightly more complex. How about a die?
Good one. A standard 6-sided die. Now the state space is 1, 2, 3, 4, 5, 6. 6 possible states. And the number of possible dynamical laws explodes. From state 1, it could go to 2 or 3 or 4 or 5, 6 feet, or even stay 1, depending on the rule we make up.
Lots more options for change. Give us an example rule for the die.
Okay, one possibility. A simple cycle. 1 always goes to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 loops back to 1.
Like a merry-go-round of numbers.
Exactly. Or another possibility.
Mm-hmm.
Maybe there are separate cycles.
Mm-hmm.
Perhaps 1, 3, 5 cycle among themselves, like 1, 3, 3, 5, 5, 1.
Uh-huh.
And maybe 2, 4, 6 form their own separate cycle, like 2, 4, 4, 6, 6, 2.
Ah, so if you start in the 1, 3, 5 group, you can never get to the 2, 4, 6 group.
Exactly. The state space breaks into separate, inaccessible islands.
That's really interesting. These closed loops, these islands, does that concept lead anywhere important in physics?
It absolutely does. It leads directly to the idea of conserved quantities.
How so?
Well, if this system is trapped in that 1, 3, 5 cycle, we could define some property, let's call it Q, that has value A if the state is 1, 3, or 5, and value B if the state were 2, 4, or 6. Since the system, once started in 1, 3, 5, never leaves that set, the value of Q would always stay A. It's conserved over time for that system's evolution.
Ah, I see. It's like a label for the island you're stuck on.
Pretty much. And this is directly analogous to real physical conserved quantities like energy or momentum or angular momentum. Systems evolve in ways that keep these quantities constant.
Wow.
And this even hints at something deeper, Noether's theorem, which connects conserved quantities directly to symmetries in the physical laws. But that's maybe a story for another time.
Okay, a tantalizing hint. So, conserved quantities from cycles in state space. Cool. Now, the source also mentions causality and reversibility as key properties.
Yes, fundamental properties often associated with classical dynamics. Causality is basically determinism again. From any given state, there's only one possible future state it can evolve into. The future is uniquely determined.
One path forward.
And reversibility means there's also only one unique past state it could have come from.
One path backward.
Right. You can trace the history uniquely, just like the future. Run the movie forwards or backwards.
So it's like a perfectly choreographed dance. Every step forward is fixed, and you can always retrace your steps perfectly.
That's a great analogy. And the consequence of having both causality and reversibility is really profound. It implies the conservation of information.
Conservation of information, how does that follow?
Because if every state has exactly one way in and one way out for each time step, no information about the system's state is ever fundamentally lost or gained as it evolves. The information just gets rearranged, essentially.
Nothing disappears, nothing is created from nowhere.
Exactly. It's a core tenet of classical physics. Though, importantly, this clashes a bit with our everyday experience of macroscopic things, where stuff seems to decay, information seems to get lost. Think about entropy.
Right, like scrambling an egg. You can't easily unscramble it. That seems irreversible.
Precisely. So that hints at where the purely classical picture might have its limits when dealing with complex macroscopic systems.
Okay, so information is conserved in the ideal classical world. But what about systems where things aren't discrete, like coin flips or die rolls? What about continuous things, like the position of a particle, which could be any value? Infinite possibilities.
Ah, yes, that opens up a whole new dimension.
Yeah.
When you have continuous variables like position, velocity, time, the state space becomes infinite.
Infinite possible states.
Right. And this led the scientist Laplace to his famous idea, sometimes called Laplace's demon.
The demon. Sounds ominous.
Well, it was a thought experiment. He said, imagine a vast intellect, the demon that could know the exact position and momentum of every single particle in the universe at one specific instant.
Okay, that's a lot of information. Impossible in reality, but hypothetically.
Hypothetically, yes. If this demon knew that exact state, and it also knew the exact laws of physics, which Laplace assumed were deterministic and reversible like Newton's laws, then, Laplace argued, this intellect could calculate the entire future history of the universe and its entire past history with perfect accuracy.
Wow. The entire cosmic movie, past and future, calculable from one perfect snapshot. That fits perfectly with causality and reversibility.
It does. It's the ultimate expression of classical determinism. But there's a huge practical catch.
I suspected there might be. What is it?
It's fundamentally impossible for us to ever know the exact state of anything continuous. To know the exact position would mean knowing it to an infinite number of decimal places.
Right. We can only measure things with some finite precision. There's always some uncertainty.
Always. And this tiny, unavoidable uncertainty has massive consequences in many systems. This leads us to chaos.
Chaos theory, the butterfly effect.
Exactly. In many classical systems, even simple ones, sometimes the smallest, tiniest difference in the starting conditions can get amplified exponentially over time.
So a microscopic uncertainty now can lead to completely different outcomes later.
Vastly different outcomes. This is called sensitive dependence on initial conditions. It's the hallmark of chaotic systems.
So even if the laws themselves are perfectly deterministic and reversible,
the system becomes practically unpredictable in the long run because we can never know the starting point perfectly enough.
Deterministic in principle, but unpredictable in practice. That's chaos.
You've got it. Mathematically, the determinism and reversibility are still there, but the amplification of initial errors makes prediction essentially impossible beyond a certain point.
Okay, that gives us a really good picture of classical physics, its structure, its concepts, its strengths, and even its limitations like chaos. Now, the source material pivots quite a bit here, taking us way back to Aristotelian physics. Why is that important? Why look at Aristotle when we're talking classical physics?
That's a really good question because obviously Aristotle's physics was largely superseded, right?
Yeah, that's centuries ago.
But looking at Aristotle is crucial for a few reasons. First, it was one of the earliest, really comprehensive attempts to create a systematic framework for understanding the physical world. It was a philosophical and physical system.
Okay, a first draft of physics, in a way.
Sort of. And understanding its ideas, its assumptions, its successes within its time, and crucially, its shortcomings, helps us appreciate why the scientific revolution happened, why Newton and others thought differently. It gives us context.
So we see what classical mechanics was building upon or reacting against.
Exactly. Plus, Aristotle's influence was just immense. For almost 2,000 years, his ideas dominated Western thought, preserved and studied by Islamic scholars. Then, in medieval Europe, it was this incredibly coherent intellectual system.
So understanding the roots helps us understand the tree, basically.
Precisely. And sometimes looking at a completely different way of thinking, like Aristotle's, can actually highlight the hidden assumptions in our own modern way of thinking about physics.
Makes sense. So let's dive in. What were the core philosophical ideas behind Aristotle's physics? How did he see the cosmos working?
Well, a key thing is that his physics was deeply woven into his whole philosophy, his logic, his metaphysics, even his biology. He saw nature as fundamentally rational, ordered, understandable through reason and observation.
Not just random chaos.
No, definitely ordered. And the basic building blocks were his four elements: earth, water, air, and fire. Each had inherent qualities and, importantly, inherent tendencies or goals.
Goals, like they wanted to do things.
In a way, yes. That's the teleological aspect we'll get to. But the point is, his physics aimed to find this overarching, intelligible order, using concepts like essence, cause, motion, and purpose. It was much more qualitative and quantitative compared to later physics.
Elements with inherent tendencies. Tell us more about this natural motion idea. How did things move in Aristotle's view?
Okay, so natural motion was tied to the element's nature. Heavy elements, earth and water, naturally moved downwards, towards the center of the universe, which he thought was the earth.
Seeking their natural place.
Exactly. Lighter elements, air and fire, naturally moved upwards, away from the center. That was their natural behavior.
And what about other kinds of motion, like throwing a rock?
That he called violent or forced motion. It required an external agent, like your hand pushing the rock. And crucially, he believed this violent motion would stop as soon as the external force was removed.
Okay. So, no concept of inertia yet. Motion requires a continuous push.
Right. The emphasis wasn't on forces causing acceleration like in Newton, but on the object's tendency to reach its natural place or being forced away from it. It's linked to that purpose-driven teleological view.
It's a very different conceptual space, not coordinates and vectors, but...
More like a quality space, defined by elemental properties in natural places.
Okay. And the document mentions a big split in his universe between Earth and the heavens.
Yes, a fundamental division.
Yeah.
He saw the cosmos split into two distinct realms. First, the terrestrial realm, everything below the moon.
Our neighborhood.
Right, characterized by change, decay, generation, corruption, and the imperfect up and down motions of the four elements.
Perfect.
Yeah, compared to the heavens. The second realm was the celestial realm, the moon, planets, stars, everything beyond.
And what was that like?
Perfect, eternal, unchanging. He believed it was made of a fifth element, a different substance entirely, called ether.
Ether. The fifth essence, quintessence.
Exactly. And this ether wasn't subject to change or decay, and its natural motion was perfect, eternal circular motion.
Circles were perfect.
To the ancient Greeks, yes. So the planets and stars just moved in perfect circles forever. This meant...
Different rules for Earth and sky.
Precisely. No universal laws of physics covering both realms. That's a huge contrast with Newton, who showed his law of gravity worked for apples and planets.
A major shift in thinking later on. What about math? Did Aristotle use math to describe all this?
Much less than you might expect, and certainly less than Galileo or Newton. He saw mathematics as useful, but primarily applicable to the celestial realm.
Why over the heavens?
Because the heavens were perfect, unchanging, eternal, and moved in those nice regular circles. That seemed amenable to mathematical description.
Geometry, right?
Exactly. But the terrestrial realm, with all its messy changes, qualitative transformations, imperfect motions, he didn't think it was really suited for precise mathematical treatment in the same way.
Interesting. So math was for the perfect, unchanging part of the universe.
Largely, yes. Plus, there were practical reasons astronomy needed math for calendars, navigation, etc., even back then.
Okay. Now, you mentioned teleology of purpose being central. That sounds really different from modern science.
It absolutely is. For Aristotle, explaining why something happened often involved its purpose or final cause, telos. It wasn't enough to say what pushed it, the efficient cause. You also had to ask what its aim was.
Like the rock falling.
Right. It falls not just because something dropped it, but because its purpose, its nature, is to be at the center of the universe. That's its final cause, its goal.
So everything has an inherent aim.
In his view, yes. Natural processes strive towards their ends. Newtonian physics threw this out completely, focusing only on forces, initial conditions, efficient causes.
No purpose allowed in Newton's world.
Not explicitly, but it's intriguing. Some later, more advanced formulations of classical mechanics, like Lagrangian or Hamiltonian mechanics, involve something called the principle of least action.
Least action?
Yeah. It basically says that a physical system will evolve between 2 points in time along the path that minimizes a certain quantity called action. It looks almost like the system is choosing the most efficient path.
Huh. That does sound a bit purposeful.
It does, doesn't it? Now, most physicists see it just as a powerful mathematical tool, a different way to calculate the motion that comes out the same as Newton's laws.
Guess math.
But some philosophers, and maybe even some physicists, look at it and wonder if it hints at some deeper, perhaps teleological structure in nature. It's an ongoing debate, even cropping up in discussions about quantum mechanics or general relativity.
Fascinating. So the ghost of teleology maybe still lingers in the mathematical formalism?
Perhaps, or at least the language we use can evoke it.
What about space and time for Aristotle? Were they like Newton's absolute background stage?
No, quite different. Aristotle saw space and time as relational, dependent on matter and change.
Relational.
Meaning space wasn't an empty box waiting to be filled. It was defined by the relationships between objects. He actually thought a true vacuum, empty space was impossible.
And void.
Right. And motion was always relative to other things, not relative to absolute space. Although he did kind of treat the Earth as a preferred reference frame, being the center.
Okay. And time.
Similar idea. Time wasn't an independent river flowing on its own. It was a measure of change, of motion. If nothing changed, time wouldn't exist or wouldn't be measurable.
So no change, no time.
Essentially, it's secondary to processes. This relational view is actually closer in some ways to how Einstein later conceived of space-time and relativity compared to Newton's absolute space and time.
Interesting connection there. What about that locality thing? Did Aristotle think things had to touch to interact?
Yes, he was a strong proponent of locality. For A to affect B, A has to be in contact with B, like pushing a cart.
Okay, makes sense. But what about, say, throwing a spear? It keeps moving after it leaves your hand.
Ah, good question. That was a tricky one for his system. His explanation was that the air pushed aside by the spear rushes in behind it and keeps pushing it forward.
The air keeps it going.
Yeah, it sounds a bit contrived to us now. It shows the difficulty. Later theories like impetus tried to address this better, suggesting the thrower imparted some internal force or quality to the object.
A step towards inertia?
Kind of.
Yeah.
But the core idea for Aristotle was contact. This contrasts sharply with Newton's gravity, which seemed to act instantly across vast empty space action at a distance.
Which bothered a lot of people at the time, right?
Hugely. Even Newton was uncomfortable with it philosophically, though the math worked perfectly. And debates about locality are still incredibly important in modern physics, especially with quantum entanglement.
It keeps coming back. Okay, you contrasted natural motion briefly before. Can you quickly recap the difference between Aristotle, Newton, and Einstein on what natural motion means?
Sure. For Aristotle, natural motion is an element moving towards its natural place, earth down, fire up, driven by its inner tendency. Anything else needs a continuous external force.
Oh, Newton.
For Newton, natural motion is uniform motion in a straight line, constant velocity, zero acceleration. That's inertia. Falling due to gravity is not natural motion. It's caused by the external force of gravity pulling the object off its straight path.
Right. Gravity is a force causing acceleration. And
Einstein changes the game with general relativity. Gravity isn't a force anymore. It's the curvature of space-time. Objects moving under gravity are actually following the straightest possible paths called geodesics through this curved space-time.
So falling is natural again, in a way, following the curves of space.
You could see it that way. It's natural motion dictated by the geometry of space-time itself, not by an external force in the Newtonian sense.
From inner drives to inertia versus force to following space-time geometry. Quite the evolution. One last big Aristotelian idea, continuous matter. He didn't like atoms.
No, he strongly rejected atomism. He believed matter was continuous, infinitely divisible. You could keep cutting something in half forever, in principle.
No smallest piece.
Correct. For him, the fundamental reality wasn't particles, but form, the essence or whatness imposed on a continuous underlying prime matter or hyle.
Form and matter.
Right. And physical objects were mixtures of the four elements, defined by qualities like hot, cold, wet, dry. Change happened gradually, continuously, through shifts in these qualities and proportions, not by rearranging discrete atoms.
Continuity was key.
Both physically and metaphysically. This is obviously different from Newton's particle picture, though Maxwell's continuous fields brought continuity back in a different way. And GR has a continuous spacetime.
And then quantum mechanics comes along.
And throws a wrench in things with wave-particle duality. Is an electron a particle or a wave? Discrete or continuous? The debate continues in different forms even today, like particle physics versus quantum field theory.
So these ancient debates about discrete versus continuous still echo.
They really do, at the deepest levels of physics.
Now, the source mentions trying to write Aristotle's physics mathematically. That sounds tricky, given how qualitative it was.
It is tricky, and obviously Aristotle didn't do it himself this way, but it's a useful exercise, kind of like translating his ideas into modern language.
Why bother?
Well, partly for teaching, to help us wrap our heads around his system, partly to check its internal consistency using modern tools, and partly to highlight the contrasts with later physics more clearly.
So how would you even start?
You wouldn't use EFMA, for instance. Since Aristotle thought constant velocity required constant force, maybe you'd try a relationship like F proportional to V, force proportional to velocity.
Okay.
Or instead of position and momentum defining the state, maybe you'd represent the state by its elemental composition, like a vector showing the proportions of earth, water, air, fire, or its qualities hot, cold, wet, dry.
A quality space vector.
Right. And then you could try to write dynamical laws for how these qualities change. Maybe the rate of change of fireness is proportional to some elemental force causing transformations.
It's an interpretation, a model.
Absolutely. It's a reconstruction using our tools, but it can offer insights into his conceptual structure and where it differs fundamentally from, say, Newtonian mechanics.
Fascinating. Using math to explore even non-mathematical historical systems.
It shows the power of the language, yeah. Allows for clearer comparisons.
Okay, we've covered a lot of ground. From the core of classical physics determinism, locality, state spaces, all the way back to Aristotle's elements and teleology. What are the main things you hope our listener takes away from all this?
I think the first thing is that classical physics isn't just done. It's still a vital foundational framework. Its concepts shaped everything that came after, and its philosophical assumptions are still worth thinking about.
It's not just a stepping stone. It's part of the foundation we still stand on.
Exactly. And secondly, understanding the historical context, especially going back to someone like Aristotle, gives you such a richer appreciation for how we arrived at our modern understanding. You see the twists and turns, the discarded ideas, the revolutionary shifts.
It wasn't inevitable. It was a process of argument and discovery.
Right. And knowing that history, those different ways of thinking, helps you, the listener, understand the physical world more deeply.
Oh, so why does this matter to me, listening now?
Because it shows you how our scientific worldview was built. It reveals the kinds of fundamental questions about motion, matter, space, time, cause that we've always been asking. Understanding the journey makes the destination, our current physics, make more sense. It gives you a better grasp of the conceptual landscape.
A richer perspective on the science itself. I like that. Okay, as we wrap up, give us one final provocative thought to chew on.
Okay, how about this? As we face the really deep puzzles in modern physics, quantum gravity, dark energy, the fundamentals of quantum mechanics itself, could there be value in seriously revisiting the assumptions embedded not just in classical physics, but maybe even in pre-classical ideas?
Aristotle. Seriously.
Well, maybe not literally his physics, but his philosophical approach. Could thinking about concepts like form, potentiality, or even teleology in a new light spark different kinds of questions, different approaches? Are the ancient debates about continuity versus discreteness or the nature of time still trying to tell us something crucial for the next breakthrough?
Could the past hold keys to the future, even in physics? A lot to think about.
Definitely something to ponder.